So today's class, we are going to continue where we left off with the design of DC motor, and then we are going to today learn about armature reaction. So whatever we are going to learn today, I don't want to get into too much details of it, but I do want to give an idea of it because the direction in which motor technology is going, DC motor is actually going to be phased out, but it's still nice to understand the working concept of it, because when we go to AC motors, whatever controls we create and everything and so on and so forth is to make sure that it operates like the characteristic curve of a DC motor. So it's important that we understand how they work, what the problems are. Right? We've already seen one of the problems with DC motor, which is basically the brushes, which are quite lossy. Today we're going to look at the other problem, armature reaction, which makes them somewhat not too compatible for when we go to very high power applications. Right? Before we proceed with today's lecture, I just have a couple of announcements. The homework is due this Thursday. Usual, the deadline is not fixed. If you want to take a couple of more days to do a better job, that's really fine, but try to submit it, not try to submit it by Friday, worst case, Sunday noon, I'll post the solutions. And so for those of you keeping track of in-class participation, this will be lecture 14 of the 13, 14, 15 series. So if you participate, you'll get the points. Make sure you make a note of it. I remember most of your names now. So even if you forget once in a while, I'll be able to mark it if I remember the name. But just make sure, in case the points aren't awarded, just send me an email and you'll get the points. Going forward, starting from this Friday, I'll start posting additional quizzes on Canvas. For those of you who haven't participated so far in class, or your in-class participation is pretty low, you can start taking those quizzes for compensation points. Those of you who have good in-class participation, you can take it if you want, but you won't get any points for it, right? You're welcome to attempt it. It'll be useful to test whether you've understood the concepts. But going forward, I'll start posting those in-class participation compensation quizzes as well. And another thing, once we are done with this lecture and tomorrow's lecture, we'll be done with the operation of DC motor, and then the next week we'll cover closed loop control of DC motor. And with that, we'll have every topic we need to do the project. Project carries 25% of your final grade. It's a pretty simple project. Those of you already doing the labs would have done half of the project already. But again, on Canvas, I'll post 4 options for doing the project. And so it will require you to come in person to the lab to do some experiments. All right, so I'll give you 4 different dates and different time options. Just pick one of the slots that you're available. And starting next week, we'll meet in the lab as well, outside of the class hours, to do the project part of it. Right? Anybody has any questions? Okay. So today's class, we are going to look at a concept called armature reaction. So last lecture, we saw how the, and before I forget, because we have Professor Shrikant and Sridharan, extremely brilliant guy. So if you ask me any questions and I don't have any answers, you're all going to look at him, right? He'll definitely have the answers. That's a lie. Right? But going forward, he would probably teach the drive course in the next year and so on and so forth. So it's nice to have him here today. Okay, so last class, we looked at how to wind the DC motor. We are looking at basic simple lap winding. We're not going to look at wave winding in this course. And we looked at the simplex winding case, where there's at any time a brush makes contact, except for the commutation portion, a brush makes contact with one commutator segment. If you have duplex winding, you'll have 2 parallel paths that will make contact with 2 commutator segments and so on and so forth. So in our case, we're looking at pure simple lap winding. So simplex lap winding with double layer. Right, double layer basically means every time a conductor goes into a slot, then a couple of turns later, another conductor would come out of the slot. Right, so that's what the double layer means. If you have a single slot and you do n number of turns in the same slot, with all the conductor going in the same direction, that does not add to another layer. All right, it's the conductor going in the other direction that contributes to the notion of double layer or a single layer. And we have the simplex lap winding double layer. That's the winding structure that we are going with. And we have, we can either use retrogressive or progressive, as we saw before. It doesn't matter which one we use. In our case, we looked at progressive. For the homework, you can either do retrogressive winding or you can do progressive winding. Retrogressive just confuses me when I draw it out. So I went with progressive, but either of those works as far as the assignment is concerned. Okay, so let's look at, for this case of winding, I'm going to draw it in the structure. In the homework, you have 8 slots. In the class, I did 6 slots. That's all the differences. Here, I don't know how many I picked. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 slots in this motor. And in the lab motor, I think it's 12 slots when we do the project part of it. So the structures, we have the rotor, the armature, and then we have the north and the south poles. And we have the magnetic fields going from the north to the south pole. This is due to just the magnetic field of the magnets alone. Right? And at every point, it's going to be perpendicular to the surface of the iron. Right? Without the iron, if we just had air gap there, these lines would have taken the shortest path. So that would be the least reluctance pathway. The preference would have been going through the shortest path for the most part. But the minute we put the iron, the perpendicular direction going from the pole to the iron would lead to the shortest reluctance path, because through the iron we assume the permeability is infinite. So here there is no MMF drop, there is only MMF drop in the air gap. So the least reluctance would be the perpendicular distance, which is the shortest distance between the two places. Okay? So this is the magnetic field due to just the magnet alone. So far we didn't worry about what the magnetic field is going to be due to the current carrying conductor in the rotor. Right? So we just looked at what the magnetic field of the magnet is, we looked at the current carrying conductor in that magnetic field, we calculated the torque, we got the expression for torque force, and then we figured out what the torque is going to be, we figured out what the EMF is going to be. This is all fine in the ideal case where we completely ignore the magnetic field that's set up due to the current carrying conductor on the rotor. In reality, the current in the rotor in itself is going to produce a magnetic field. So if you have a current carrying conductor, throw your hand around it, okay, and all the components is going to be purely tangential. We saw the reason for that as well, because divergence of magnetic field is zero. They can only be tangential component. So this is going to be the magnetic field due to a single conductor. And when we look at all of these set of conductors, it's going to be basically these field lines that are created by these conductors, which have this effective magnetic field. And this is called armature reaction when it interacts with the external magnetic field that's being generated by the magnet, right? So without this would have been the ideal way in which the magnetic field would have been, and the center point is called the geometric magnetic axis, right? And this is where the EMF would have been zero as well. Whichever coil was in this position is where the EMF would be zero. What is going to be the flux across this coil? Is it going to be zero or maximum at that point? For the coils at 90 degree, is the flux through the coil at its maximum or at its minimum?
Maximum.
Maximum. So at this point, the flux is maximum. But the EMF, which is d phi by dt, that is going to be zero in the ideal case. And why do we want the EMF to be zero? What is happening to the coil at that 90 degree location? What was it?
Being shorted.
It's being shorted because this is the coil that's undergoing commutation. So the windings are being shorted, this one and this one, by the commutator segments. Okay. Two adjacent coils are being shorted by the commutator segments. So whichever coil is undergoing the commutation, we want that EMF across it to be zero. Otherwise, there's going to be a huge amount of current that flows through the brushes, and it's going to damage the brushes as well as the winding in the long run. So you want to make the EMF zero. But what happens is due to the magnetic field created by these current carrying conductors on the rotor armature structure, there's going to be an additional magnetic field that's created. So the net magnetic field experienced by these conductors will be the sum of these two magnetic fields. Right? So you can do some FEM modeling and sum these up. And this is what the structure of the magnetic field lines that come out of it would look like. So just to quickly check what's going on, if you look at this portion, right, you curl your hand around. So the direction in which I've drawn these field lines are correct for these two cases, right? Here it will be in the clockwise direction, here it will be in the anti-clockwise direction. So if you look at on the top portion, you have magnetic field coming from north to south due to the magnets, and then due to the current carrying conductors in the opposite direction, effectively weakening the magnetic field under one half of the pole of the magnet. In the other half pole, so the magnetic field due to the magnet is going from north to south, going in this direction, and the field due to the current carrying conductors on the rotor is also along the same direction, strengthening the magnetic field. The same thing on this side, if you look at it, the magnetic field due to the external magnet is in this direction, and the field line due to the armature reaction is in the same direction, adding on to it and strengthening the magnetic field in that location. And here, it is in the opposite direction, right? It's returning, while due to the magnet it's going in this direction, therefore subtracting away. So you can effectively sum these. These are not just basic summations, because these are vector fields. So you need to do vector addition. But at the end of the day, when you do that, this is what the effective field lines will look like. Now, this is quite a bit problematic because if you look at the vertical point, which is where the commutator segment is shorting two coils. Previously, our field lines, our flux did not change as we went from a small angle before the angle at 90 degree and small angle after 90 degree. The change was minimal in the flux. That is what led to the EMF being zero. But at this point, there is a significant amount of flux change because these flux lines are no longer perpendicular to the coil at 90 degree. Here, the flux lines are perpendicular to the coil at 90 degree and d phi by dt ended up being zero at that point. But here, the flux lines are no longer perpendicular. So as this angle changes from some angle just before 90 to 90 degree, there is still some flux lines which are changing, field lines, which is then going to lead to an EMF that's being non-zero. Right? So where is that EMF going to be actually zero in this case? It is again going to be the case where the loop is perpendicular to the magnetic field lines. Right? It's going to be slightly shifted out by some angle delta. And this newly shifted location is called the magnetic neutral axis. So what is now going to be the problem because of this? What is going to be the issue? Our commutator is still here though, right? Our commutator hasn't moved. So now when the coil is at 90 degree, the commutator is shorting the coils, but unfortunately the EMF across the coil is not zero. So there's going to be a huge amount of current that goes through these coils, through the graphite brushes and start to eat away at the graphite brush, as well as damage the coil if the current ends up being too large, right? Which can be the case when the motor operates at very large speed because the EMF induced is not negligible even at those angles very close to 90 degree. Can anybody tell me what the solution for this would be? There's a rather easy fix. Any ideas? Yeah, Thomas.
Move the brushes.
Move the brushes. Perfect. So we can shift the brushes, which is a very commonly used solution, especially for low currents application, small motors. Typically, you will see these brushes when you open them out. They won't be exactly at the way the winding works out, as we saw in the winding diagram. The brushes in the physical motor would actually be along this axis. They wouldn't be exactly at this axis. They would be slightly shifted out, right? So that's basically doing the shifting in this effective equivalent circuit diagram that we're drawing here, effective equivalent diagram we're drawing here. So once we have shifted this out, now we can ensure again the EMF along this axis, the coil which is along this axis will be zero, so we can short it and get away with it. What are the shortcomings of this method? Yep.
Would the axis change depending on the current flowing through the conductors?
Perfect. So depending on the direction of the current, first thing, if the current direction were to flip, right, we're operating as a motor and then we say we want to do regeneration, we want to change the direction, then the current direction is going to flip around and basically this becomes negative, this becomes positive. So this would strengthen here and reduce here, basically mirroring the magnetic neutral axis. Or even if the current starts to increase or reduce, if the current is increasing, this axis is going to move farther out. If the current is reducing, it's going to go closer to 90 degree, right? Because if the current is zero, it will go to exactly at 90 degree, which is the original case, with purely the magnets alone. If the current starts to increase, it's going to move farther and farther out. So even if you shift the brushes, it is only for one particular operating current. And the solution works if you have, like, say, a traction application, like trains or something, where you have a motor that's always going to more or less in the steady state run at some constant speed with transition happening whenever there is a stop or something, which is very relatively small portion of the time. Then you can go with this arrangement where you put these brushes in the shifted point and get away with it. But in real motors where you have continuously changing speeds and stuff, this would not applicable. The continuous changing torque condition, this would not be a very good solution, right? So let's look at this in a little bit more detail, what's going on here. So let's start off with the case here where we have the magnet, we have our rotor structure, and we are going to look at what the magnetic field in the air gap is going to be. And the notation that I'm going to be using is if the magnetic field lines are going from stator to the rotor, I'm going to consider it to be positive. Different people use different conventions. That's totally up to you what you want to use. But this is the convention I'm going to use. So if the field lines are going from the rotor, stator to the rotor, we're going to call it positive, and rotor to the stator, it's going to be negative. Again, the concept of field lines going from north to south is again just a convention. You can draw the field lines in the reverse direction and confuse everyone, but that's absolutely fine too. Okay, so if you're looking at purely just the magnet alone, what the magnetic field is going to be in the air gap. For angle, so this along this angle, I'm going to call it a 0 degree. And as we go higher and higher, let me draw it the other way now, because that's what I drew there. So we are going in the clockwise direction, right? So this angle is going to be 0 degree. And then as I keep increasing, we are going to go to higher and higher angles. So at 0 degree, right, the field lines are going from the north to the south pole, now north to the stator to the rotor. So my B is positive. And once I hit 90 degree, the field lines are going from the rotor to the stator. So this is going to go negative, and then we go on and go on and go on. From 90 to, I should have gone a little bit symmetric. Right. So once we go from 90 to 270 degree, 90 degree, all the way to 270 degree, we have negative field because we are going from the rotor to the stator, and then the reverse of it again, right? From 270 to 0 degrees, we have the rest half of it going from the stator to the rotor. So this is a magnetic field purely due to the magnets alone. Now we want to figure out what the magnetic field due to the currents in the rotor is going to look like. So I'm going to give you the diagram. This is what it's going to look like, and then we'll figure out how to find out the values for this. Right? Anybody have any questions so far? Yep, Thomas.
Why are we not doing the cosine alpha anymore?
What was it? Why are we doing what?
Cosine alpha? Like, why is it not a?
Oh, that's a very good question. So so the reason we are not doing a cosine of alpha is when we have. So we will rederive the equation for Ke and Kt in this new arrangement. But in the previous case, we were looking at the case where we had a coil, conductor coil in air, and we had magnetic field lines going straight from the north to the south. Right? As this coil rotated, the flux through the coil is changing. And if you look at this coil, so we had this coil like this, and then we had some B field here, the current is here, there is going to be some force that's produced in this direction. Only a component of the force is torque, the another component is basically pulling the coil out. And the component of force that's producing the torque we represented with the cos of alpha tau. And the same thing when we looked at the flux, as the coil is rotating, when it's at a 0 degree angle, no flux is linking it. As it's rotating, more and more flux are linking at 90 degrees when all the flux are linking. But when you have the case where the whole structure is put inside an iron core, the B field, irrespective of where the conductor is always perpendicular to the conductor. Right? In this case, that wasn't the case. So when you had the B field like this in the air gap and a current carrying conductor in this angle, the B field was not perpendicular to the conductor. Right? So at least the torque that was produced due to the B field was not perpendicular at every single point. But in this case, because we introduced the iron structure, the B field is going to be always perpendicular to the structure of the iron. And we looked at why this is going to be perpendicular a couple of lectures back. Anybody remember what was the reason we gave? Why do all field lines terminate perpendicular to the iron?
There's no monopoles.
What was it?
There's no monopoles.
There is no motor, even in this case, right, there is no monopole, but the field lines didn't perpendicular to the structure of the coil, right?
Least reluctance.
What was
Least reluctance.
it? Reluctance. So there are multiple ways you can prove it. So the path of least reluctance would be the direction where it maintains the least amount of time in the air gap and rest of the time in the iron, right? And that will be the perpendicular direction. So the shortest path between 2 points is the perpendicular distance. Sorry, shortest path between 2 lines would be the perpendicular pathway between the 2 lines. Or another way of proving the same thing would be, let's say you have this iron, and we can draw a tiny loop on this iron. And if I go around and integrate the H field here, let's say it's H1 here, H2 here, H3 here, H4 here. If I go around and integrate the H field here, that's going to be, let's say this distance is L1, L3, L2, and L4. H1 L1 plus H2 L2 plus H3 L3 plus H4 L4 must be equal to, in this case, what will it be equal to? What will the integral H dot dl in this case be? I just have an iron material and I'm drawing a, so I have an iron material, this is iron, this is air, and I consider a loop here. and I go around and integrate the H field around that loop, what is the value going to be?
Ni.
What
Ni.
Ni, what is Ni in this case? Have I drawn any current carrying conductor there? No, right? There is no current carrying conductor here. So Ni is just going to be equal to 0. So this whole term is 0. Now I can make this loop tinier and tinier so that this L to L4 distance becomes very close to 0. So that we have one line in the air gap and another line in the iron. So L2 and L4 term goes to 0. So we are left with H1L1 plus H3L3 is equal to 0. And again, if these are, we have looked at it as if these are arcs, but as this distance starts to collapse, L1 and L3 becomes same. Sum L, H1L plus H3L equal to 0. What is H in the iron? You all did this in the experiment, homework and everything. Let's say the permeability of iron is infinite. What is H in iron? 0. So the H3 term goes to 0. So what is the only solution? H1 must also be 0. Right? So tangential component of H field in the air gap is 0. If the H field in the air gap is 0, what is the B field in the air gap? 0, because B in the air gap is just mu naught times H. So B in the air gap is also 0. So there is no tangential component of B field on the near to the surface of the iron. So the only component that can exist is the perpendicular component, right? So you can think of it as the shortest distance, or we can think of it as purely mathematical from the equations that we have. Either way, the proof is that the flux lines are always going to be perpendicular once we introduce the iron. So at every single point, these field lines are perpendicular. So the torque or the force on the conductor at every single point that's produced is going to be in such a way that it's purely tangential component. All the component of force is only tangential. There's going to be no normal component. And this is what I mentioned in this the diagram that we drew. I said that there is going to be an enormous amount of forces that are created on the winding. But in a practical motor, you do not even have to have too much of a retention sleeve or anything to counteract this force, because that force would not exist at all in the first place in an actual motor. We still do put the retaining sleeve because of the centrifugal forces, but not the normal force, because the normal force dissipates away completely because it's always perpendicular. Right? So the cos alpha term, that's the reason it disappeared. Right? Any other questions?
Just to clarify about the graph, so BM is flipping, that's because of the commutator, right?
BM is what?
Is like flipping at 90 because of the commutator?
No, BM is not because of the commutator. BM is flipping because the direction of the flux change.
Oh, okay.
Right? Here it's going from the stator to the rotor, here it's going from the rotor to the stator.
And then this BA, is that the, like, what is BA?
I'll get to that in a second. BA is due to the magnetic field in the air gap due to the current carrying conductor. And we'll figure out how to get those values in a minute. Okay. Any other questions? Okay. So let's first I'll give you a couple of loops, and then we'll figure out what will happen if I choose a different loop to calculate what the H field in the air gap is due to the current carrying conductor on the rotor. So let me draw a bunch of loops. Let's say I have a loop like this, and let me call this H1, H1. Let me call this H1, H2. And finally, again, it should always be perpendicular, even if my drawing doesn't look like it. Just remember that it's perpendicular. Of course, that does change when the core starts to saturate and it starts to behave more like air gap, in which case the perpendicular constraint starts to disappear. Okay, so for the first loop, if I go around and integrate the H field, what is that going to be? Let's say the air gap length is Lg. And let's assume for now the air gap length is uniform across the full motor, which we wouldn't use for a practical motor as we'll look in a second. But let's assume the air gap length is Lg always. There is no saliency. Right? Again, I'll need to address what the term saliency means. Okay, so what will be the, if I go around and integrate the H field here for the black loop, what would that mean? Integral H dot dl.
0, there's no current.
0, there's no current, perfect. So, and again, we already made the assumption that the core is not saturated, so in the ion, H is equal to 0. So we just have H1 times Lg going in this direction, and then coming out in the other direction, H1 times Lg. I'm making a very big assumption here. Someone can point that out, that will be great. But for now, the H1 is 0. Okay. What will be for the second loop if I go around and integrate the H field? Let's assume each of those dots represent just one conductor each, right? What will it be?
2i.
2i. So my H2 going by the same process that I have there, it's going to be 2i by Lg. Rest of it is pretty straightforward. It's going to be 4i by Lg. And then 1, 2, 3, 6i by Lg. Oh, by 2 Lg, right? Sorry. So because this would have been H2 Lg plus H2 Lg. One being here, one being here. I'm going to drop in two places. So 2i by 2 Lg or I by Lg. This would have been 6i by 3 Lg. Sorry, 6i by 2 Lg. And then the purple would have been H3 is 4i by 2 Lg. So in this portion, right, at alpha equal to 0, go back to this diagram. Our H was 0. And then as we keep going upwards, right, we have H fields going in the reverse direction. And then as we complete this full turn, we come back. The same thing can be recreated here as well. Draw the same loops. Right? If I draw the same purple loop here, and then we have current going in, you can do the same thing here as well and get the same diagram that we have there. Right? So due to the magnetic field of the conductors, we have H field that are going on one side of the pole. It is adding on to the magnetic field. On the other side of the pole, it's subtracting away from the external magnetic field. Right? So we have our external magnetic field here. So our magnetic field due to our rotor magnets are going in this direction, going from north to south, right? So for one half of the pole phase, these magnetic field due to the armature currents is strengthening the magnetic field. In the other half of the pole phase, it's weakening the magnetic field, right? This effect is called demagnetizing effect. Demagnetizing effect or cross-magnetization armature reaction. Okay. And the reason we are calling this as cross-magnetization armature reaction is when we go back to our original diagram here. If you look at the component in the iron core, the B field is perpendicular to the component of the external magnetic field. So any magnetic field that lies along the external magnetic field, the direction or along the x-axis, we are going to call it the direct component. Anything that's perpendicular to it, we'll call it quadrature or the cross component. Right? So this magnetic field due to the armature reaction has this cross component, but it has a demagnetizing effect as well. Right? Due to pole shift, there will be another demagnetizing field that's induced, which is completely different from this. So the terminology does get a little bit confusing there. Right? So half of the pole phase, the magnetic field strengthens, half of the pole phase, the magnetic field weakens. The same thing happens on this side as well. Half of the pole phase, the magnetic field will strengthen, and this half of the pole phase, the magnetic field will weaken. Right? So let's go back to this diagram now. Right? I know I should have drawn the polarity in the other way direction, but think of the current being reversed. I don't want to erase this now. But the concept is what matters for us. Okay. So as we go farther and farther out, more number of loops are encircled. That means the more number of H, more integral H dot dl component will be there, and more H in the air gap is going to be there. And if the H starts to increase, the B is also going to be increasing. Assuming again nothing is saturated in the system, it's going to linearly increase and it's going to reach its peak. And where is that peak going to be? It's going to be peak at this point where all the conductors are being enclosed by the loop that I have. Right? When the B field due to the external field is at its zero, that's when the B field due to the armature component ends up being the maximum in the air gap. And it's going to be zero when the B field here is the maximum. That is when the B field due to the armature, due to external magnetism is maximum, the armature B field is going to be at its minimum at that point. Okay. So this is the B field due to the in the air gap due to the armature winding. This is the B field due to the magnet that we have.
This might be a stupid question, but like, do they match on the top and the bottom? Like, is that the max at both the top one and the bottom one, or just the top one?
Which matches? I didn't get it, sorry.
You just said that, I think it was B, was peak at the top one because all of them are.
Oh, okay. Yeah, no, it's the opposite. It's 90-degree phase shifted. So due to the external magnetic field, the B would have been the least at this particular 90-degree point. Right? Because that's where it flips going from the north to the south. Right? If you look at this diagram here, B goes from north to the south at that 90-degree angle. But that's when the magnetic field due to the external, due to the armature current is its maximum. Right? So when it's at 0 degree, the B field due to the magnet, if you do the Fourier components for this, the maximum would be at this point. But that's when the armature component becomes the 0. Right? They are phase shifted. Any questions? Okay. So now the net magnetic field in the air gap that is being perpendicular to the conductor at every point will be the summation of these two, assuming that the core hasn't saturated. So let's do the summation and see what it looks like. Let me draw it on this itself. So at this point it's 0. So what I'm going to be drawing is the summation of, so purple is summation of BA plus BM. Assuming the superposition applies, which it doesn't in reality. So if there is no saturation, go ahead and apply superposition. So we are going to add this and this together. So this black waveform plus the second black waveform is going to add up. Okay. And then reach this point here. And so on and so forth. Okay. So it's basically just the sum of these two waveforms. So we can already see the problem that's occurring here. Right? So we have a delta shift in where the magnetic field in the air gap goes to 0. Right? Previously it was at 90 degree, which is what we wanted it to be at because that's where the commutator initially was. But due to this armature reaction, that position where it goes to 0 degree gets shifted out. Okay? So our commutator position has to be shifted out as well, so that is where the coil that's being shorted happens when the flux to that coil is at maximum, but the d phi by dt, so the coil d phi by dt would end up being minima, so that the magnetic field, so that the EMF across the coil goes to 0 when we make the short circuit. Right? So everybody clear on this point? What happens? Yep.
Maybe I'm missing something, but are we like ignoring the H field inside the magnet itself?
H field inside the magnet. Yeah, we're going to assume this is a ferrite magnet, or if it's a salient pole, like it's a wound, we have like an iron core on which coil is wound, it's an electromagnet. So we're going to assume that has infinite permeability as well. So if we have neodymium magnet, the situation becomes a little bit trickier. All right, there would be no saliency, which we will introduce later in this magnet, that would not apply when we have a neodymium magnet in this place. All right, for the motor that we have on the table here, we do have an Alnico 5 magnet inside. Okay. Any other questions? Yeah, so we are going to assume that the core is of the magnet as well as infinite permeability, which is not an ideal assumption, which is not a real assumption either, but we are going to go ahead with it for now. Right? Everybody clear on this part? The summation? Okay. So there are a couple of solutions. So the one solution we can do is, of course, shift the magnetic axis, but that then has its own problem where it only applicable for particular current and particular direction of current as well. So there is a nice solution in practical motors. What we do is we try to reduce the effect of this armature reaction at this angle, at where we want the commutation to happen. We want to reduce the amount effect of this magnetic field, the armature current on the magnetic field that's created in the air gap. So one way we achieve that is by making sure our poles do not have a full 180-degree coverage. So if you look at the poles there, the way I've drawn it on the board is not the same way the poles are there. So once I put the rotor structure inside, you can see that some of the conductors on the top do not get covered by the full magnet. Right? There's a portion where the magnet does not cover the full set of coils, the rotor armature slots that we have. And this creates what's called a saliency. So what happens in this new structure is first, this magnetic field does not have a vertical drop. Again, and even in reality, if you had full 180-degree coverage, there wouldn't have been that sharp. But it starts dropping much sooner. Okay? Because this magnet is no longer doing this full 180-degree coverage, but rather has a shorter pitch. Right? So the magnetic field here takes a longer pathway. And we already saw what happens when you have larger air gap, the magnetic field, the load line starts to have a slope that is much lower. So the where it intersects the magnet becomes much way down in the low B field or much higher H value, negative H. So the B field here would be much, much lower and weaker. So as long as the absorbing manner. So we get one advantage from this, the fact that when we short the commutator segment, right, it is not shorting only at 90 degree. Even before at 90 degree, there is some portion that has started to short away. Right? There is some portion of contact that is already made even before 90 degree. So it would be beneficial to make sure that the magnetic field is much lower even before 90 degree, not just at 90 degree. Even before, if you start to reduce the magnetic field, the induced EMF will be small enough that it doesn't cause too much current to flow through the shorted pathway. So we do get that advantage by reducing the pole phase. But the biggest advantage that we get is this waveform that I had for the B field is no longer going to look like this. We are going to significantly reduce the peak of this B field by just introducing this additional length in the air gap, the saliency that we have, because our H is still the same. H does not change. Right? LG has now increased in that equation that we had there. It was same H1, H2 there. So going back to this, our equation, when you solve this, these two would have been the same H1, H2, H3. But if you look at the H4 pathway, so the magnet has now reduced. Right? Now, if you look at the H4 pathway, it's going to have to take a much, much longer pathway to go to the stator core. So let's say we have a stator core surrounding the structure. So the LG length for the H4 pathway has increased significantly. Right? So here when we had this would not have been same LG as before. This would have been a new LG, LG prime. LG prime is much, much greater than LG. Right? So this structure is called saliency, where different pathways for the magnetic field have different reluctances that are associated with it. Right? When the air gap length increases, the reluctance increases. So there is hesitancy for the fields to go through that pathway. Thereby the B field, the H field will become lower, and then the effective B field is also going to be lower. So B there is going to be just mu naught times H4. So if H4 goes down, B there also goes down. Right? So previously O was looking like the sharp peak. That would now become much, much lower because we increased the reluctance of the pathway very large. Right? It's the same N9. The right-hand side does not change in the path, but the left-hand side of the LG part changed, thereby reducing the B field effectively, or reducing the H field, and in turn reducing the B field. So what do we get out of this? This curve, the summation, is not as drastic as before, significantly subsidized. So it starts to drop off much earlier. It still goes to 0 at the 90-degree point. But it does not reach the peak as much as it did before. So the delta angle is much reduced. So we are closer to the geometric neutral axis compared to the previous case. Previous case, it was farther out. Right? In this case, we're just a little bit closer than what it was before. This would be the new delta prime. So this is what we get. So even when we have, typically you would see the structure in DC motors that are wound field. So you have the structure on which instead of using a magnet, you would basically use a field coil that is creating the electromagnet. Right? And these structures would be again iron. And here the mu r is pretty large. Right? Mu r is close to infinity. So the field lines here particularly makes much more difference whether you have saliency or you don't have saliency. When you have magnets, if you have a neodymium magnet, it absolutely doesn't matter whether you have a full spread or no spread for the armature reaction component. It still matters for this BM component, it doesn't matter for the armature reaction. When you have a ferrite magnet, it does matter, not as much as this iron core, but it's still not as bad as a neodymium magnet because the mu r around the operating point is around 100 for a ferromagnetic material. For a neodymium magnet, mu r is around 1. For iron core, mu r is around 6,000. Okay? So it still matters for ferromagnetic alnico magnets, ferrite magnets. Right? Anybody any questions on this part? So very clear how we can address armature reaction to some extent by using saliency. Okay. Is there any other way I can achieve the same thing? So I have some B field here. I want to reduce the B field here. Can somebody tell me? You can modify the motor however you want. You can introduce new things. You can put new poles. You can put new windings. You can do whatever you want for this motor. Can I get the same effect of reducing this B field by any other method? So if you have some B field and you want to counteract the B field, what would you do? Yeah, Thomas.
Can you decrease the current running through the coils that are like close to?
So in a DC motor, we have only one control of current outside.
Well, you said we could change anything.
Yeah, we can change anything, but we still want to make it to operate as a DC motor. Though.
Okay.
Right? We don't want to have like multiple legs. With a power, you are on the right track though. You want to put some other extra set of windings to create some other different current, right? Which is not, we don't want to modify the rotor structure though, because you would have to put extra commutator pathways, extra brushes, and so on and so forth to do that. What else can be modified? Well, we can put a magnet. Let's say I put a magnet here and a magnet here. North and south here. Right? So the B field spiked at that point. Now basically I create a magnetic field in the opposite direction so that I get the same effect as suppressing the peak that I have there. Right? So if I had a magnet here which is creating a magnetic field that's in the opposite direction, that would effectively just suppress the peak that I saw there. So those are called interpoles, and we won't use a magnet per se. We will use a winding. So we'll have this structure and we'll have some winding. And the current would come from the commutator brush, go into this interpole, and then this is what would come out as the positive terminal of the motor. And then on the same side here, it will come out as negative terminal of the motor. So you'd instead have an electromagnet to create the same magnetic field. Why don't we just put an actual magnet instead of using this electromagnet? What do we gain by using this electromagnet instead of a fixed magnet?
Are we able to control the value of the B field in that area?
Fantastic. So because for different values of current, so if I had a lower current, I do not want to compensate it too much, right? I don't want to make this go the other direction. All I want to do is reduce this as close to zero as possible. So depending on the current magnitude that I have there, the amount of magnetic field that's compensated must also change. And that's the reason I connected that in series with the actual rotor current that's coming out of the armature. Because the rotor current increases, then that current would also increase in the interpoles, therefore creating a stronger magnetic field that would push it way down. If it is very low current flowing in the rotor, then the interpoles would have very low magnetic field so that it doesn't push it hard too much down in the other direction. Right? Very clear? Okay. So we have addressed one problem where we wanted to get the field there as low as possible during the commutation instant, so that the EMF built up across it is as close to zero as possible. Is it sufficient if the EMF is zero for commutation? What does need to be zero at the 90-degree point? When we looked at the case of improper commutation, what was the problem? The current in the coil not being zero, right? If you have the current in the coil and the commutator segment, the brush segment moves past the commutator segment while there is still current, then you're going to break an inductive coil, cause a huge amount of current, huge amount of LDA by dt, which is going to cause an arcing. Right? Oh, I should have brought the video for it. Next week, on Friday, I'll show you the video of arcing. But that's the problem. How can we address it? So even if the voltage is zero, the current is not going to be zero. So the way we looked at the circuit, equivalent circuit, we have some resistance of the brush. And then coil itself, we are going to assume negligible resistance compared to the brush. So this is the commutating coil, which is basically a whole bunch of windings on an iron core. So it has quite a bit of inductance into it, right? So if you look at our voltage versus current, voltage as a function of time. And if you look at our current is going to be lagging our voltage. And the amount it lags is going to be tan inverse of omega L divided by R. Okay. So this is the angle by which the current is going to be lagging. So even if our voltage has gone to zero, our current is not at zero yet. Right? If it's purely inductive, the brush resistance is very low, then it's going to have a huge amount of current. So one way of addressing the problem with commutation is actually putting a very large brush with a very large resistance. And that's one of the reasons we do use graphite. There is another option as well. We can use a copper brush. Right? But the copper brush offers very low resistance, which means that the current will be at very large value where the voltage is at zero, and then that means the commutation would be delayed. So this is what the current is going to look like. Let's say this is 10 ampere, it needs to go to negative 10 ampere once the commutation is complete. At 90 degree, we would want it to go through zero just for the symmetry of it, right? But if this is a copper brush, this is going to take a very, very long time to decay. And it wouldn't have gone to negative 10, the current direction would have flipped. So this part would break LDA by dt, causing the arcing. But if you had a graphite brush, it will be mostly resistive. So the current would be closer to the voltage. Right? So the amount of current that still needs to reduce to zero is much lower than before. So this would be the case if we had a copper brush, this would be the case if we had a graphite brush. Right? So LDA by dt here can be reduced. So why don't, still a lot of motors use copper brush, why don't all motors use graphite brush? So you do get this beautiful advantage. The larger the resistance, more closer it becomes. You can get away with just having all our regular things. We don't have to worry about, the magnetic axis shifting and all of those. Okay, but why do we still use copper brushes? Sorry, copper brushes. Yep, Leo.
Would possibly be like economics in terms of how much it costs or how long it lasts doing this?
Copper brush does become more expensive than graphite brushes, right? But we still end up using copper brushes though. Yep.
Is it due to like the longevity of the
The
material?
longevity. The graphite does wear out. Copper also has so when the graphite wears out, in both these cases, what we do is we put the commutator segment, brush segment on a spring that keeps pressing against this copper brush that we have. So even when you have the copper brush, this would keep pressing against it and it will still keep making contact. And the wear out rate of copper brush is lower than the graphite brushes, but it's not appreciably lower to make the justification. And what is the biggest problem with having the graphite brush? Its advantage ends up being its disadvantage as well. It has quite a lot of resistance. Right? That means the current flowing through the armature on all the coils, not just the commutating coil. right? It's going to drop a huge amount of power in this commutator brush that we have. So if we had a graphite brush, so the current not only flows, so when we had our equivalent circuit diagram that we drew, let's say there is a commuting coil, and this is what it was shorting. For the coils that shorted, having this large resistance was helpful because the current was in phase with the voltage. But for the coils, otherwise during normal operation, for coils that are not commutating, or in the case where this is shifted around and none of the coils are commutating, the current is still flowing through this graphite brush, which has very large resistance, right? And then I square R losses becomes very large, a significant amount of power is lost in the brushes. So this is graphite brush is feasible when you have high voltage motors or low voltage, but with very low currents. When you go to very high currents, typically for like traction motors, or used in like old trains and stuff, you cannot use a graphite brush anymore. You have to use a copper brush in the skin because this drop would be too large that you can't manage the thermal within the space that you have, right? So we do get this advantage with graphite, but it has its own disadvantage as well. Okay. Right. So let's go back to our drawing here. I did lose my train of thought for a minute. Okay, so we are thing is we can put a, depending on the increasing the resistance of the brush, we can reduce our armature we can reduce our DEI by DT term, thereby reducing the arcing that we have. And so the other option is we can use the interpole, we can use saliency, and there's one more option that we have called compensation windings. So let's go back to this diagram here. Right, so when we had our so we saw that because of this, there are two problems that we have. So when we have these coils, we saw the magnetic field that's generated by these coils is gonna be strengthening it on one side, reducing it on one side. Right? In this case where we have the brush in the center, so the conductors on the left all have currents going on one side, conductor on the right have all currents going on the other side. Now, if we have this, when we assemble these motors, there are two problems. Either we can intentionally phase shift the axis so that the commutator segment is no longer at the 90-degree point, but at some angle slightly shifted away intentionally, or it can be an unintentional consequences as well. As the rotor rotates, the brush position can shift a little bit. Or even during assembly, it is not particularly possible for large motors to make sure that the angle at which the brush segment is at exactly 90 degrees. So if it's slightly shifted, then what would happen is the current on the right side of the commutator segment is always going to be one direction, and the left side is going to be in the other direction. Okay, so this is going to have current going into the board, and these two are going to have current coming out of the board. So let's look at the magnetic fields of these two set of coils, and then the rest of these set of coils. Okay, so you're going to break them out into two set of separate fields. Okay, so what is going to be the magnetic field due to the coil here? If you go put your hand like this, curl around, you're going to have magnetic field in this direction, and because of this set of coil, it is going to be in this direction, right? So we are only looking at the two coils that are out of place because of our shifted magnetic neutral axis. Right, so these two coils alone. So because of this, we have a north pole, we have a south pole, we have magnetic field lines going from a north to south pole. The magnetic field due to these two set of coils, previously when we had our magnetic neutral axis exactly in the 90-degree point, the conductors on the left created magnetic field going vertically down in the core, and the conductors on the right created magnetic field going vertically down on the core. right? In this case, there are two set of conductors that are actually creating magnetic field going the opposite direction to the magnetic field due to the magnet. The rest of them would still create the same thing as before. Going perpendicularly down, going perpendicularly down. Alright, so the other two are still cross-magnetization field. These two coils are creating direct magnetization fields because of our misplaced position of our commutator segment. Right? Everybody clear on this part? The two coils that we have out of place. Okay. So this is going to reduce the magnetic field due to the external magnet. If you look at the direction of these magnetic field, these are opposite what the magnetic field of the external magnet is creating. Okay. So this is called demagnetization effect. Direct magnetization of armature reaction. This is particularly problematic in a motor. So previously we saw the demagnetization effect due to the cross-magnetizing field, right? This demagnetization effect. But now this is a bit more problematic because let's say there is some torque in the motor and we have excited it by some voltage V, right, which is fixed. And there is some current flowing and now the torque on the load, let's say it increases. Once the torque on the load increases, the current in the armature has to increase. Right? If the current in the armature increases, what is going to happen to the B field in the core? Would it also increase or reduce? Due to the external magnet, the B field is still going to be the same. But due to these two coils, the current in these coils has increased. What's going to happen to the magnetic field due to those coils? The current in the coil increases. What's going to happen to the magnetic field?
Decrease.
It should decrease. So the current to the magnetic field due to these coils are going to increase, but it's the opposite direction to the external magnetic field. So the magnetic field effectively in the core is going to reduce. So our load torque increased, because of which our current should have increased, but because of which the magnetic field in the core starts to reduce. If the magnetic field in the core starts to reduce, what happens to the electromagnetic torque?
Decreases.
Decreases, because we saw the formula RLV NC divided by 2 times current, right, which we derived a couple of lectures back. So our electromagnetic torque goes down. If our electromagnetic torque goes down, what happens to the speed of the motor? There's some load torque being applied on the motor and your electromagnetic torque is reducing. What is going to happen to the speed? Decrease. So our omega mechanical is going to reduce. If omega m reduces, what's going to happen to the EMF? What's the relationship between the back EMF and the speed of the motor? K times omega. Right? So if omega reduces, back EMF reduces. Now comes the tricky part. If the back EMF reduces, what happens to the current? Increases, because this is fixed. This term reduces. So V minus E, since E reduced, V minus E term would have increased. So V minus E equal to LdI by dt plus Ri, assuming that since it's steady state, ignore this term. So I is going to increase. Right? So I is going to increase. We have set up a cyclical loop. Now again, this I increases, B starts to reduce, and it gets compounded even worse because as these B starts to increase, the core starts to saturate more and more and more. Right? So the amount of reduction in the B starts to increase as well, or even though the I is increasing. So then the B reduces, and then the tau EM reduces, omega reduces, E reduces, I increases, and becomes a cyclical loop, especially in very high power motors, where when you go to very large rated torque or slightly above rated torque, it goes into a stall condition where it abruptly comes to a stop. So this goes into an unstable operating point. So this demagnetization effect of this direct magnetic field is extremely problematic in very high motors. Okay? So let's look at just one more compensation method. And with that, we will be done. Okay. So we looked at shifting the brushes. Shifting the brushes works for one particular eye. and either motoring mode or generation mode. You need to decide which one you want to do it for. Right? If you change, the current direction changes, so the I particular is no longer the same current and would start to fail. We can use interpoles. Okay, so using interpoles, we can compensate for any current. And we can do one more thing. Oh yeah, that's where I lost my train of thought here. Okay, so we can do one more thing with interpoles, which is that when we have our voltage and we had our current, right? We wanted this current to be zero. Let's say our 90-degree point is here. Right? We wanted this current to become zero when we are at 90 degree, when the commutator segment is at 90 degree. And the brush segment is at 90 degree. There is equally shorting both the commutator segments. So one way we can achieve that is either increasing the resistance of the brush, right, so that this gets closer to this way, or what's another thing that we can do? Is there anything else we can do? I want to shift this current to go backwards. What else can I do? Well, if somehow I can shift the voltage to go backwards as well, I can move the current back for the same given R and L combination. So let's say this is my 90-degree point. This was initially my voltage, and this was my current. Now, if I shift the voltage back so that it goes zero at much earlier point, then the current would also be shifted so that we can get it to go back to 0 degree at a much earlier point, at the desired point that we need. So this is what interpoles can let us do, because not only can we compensate for the armature reaction, we can in fact make it go a little bit further down. So we can make this much stronger so that this is not only going to remain very close to 0, we can actually make it very large such that it dips even negative. So what will be the net sum? Net sum, we can not only make it go to 0 at 90 degree, we can actually shift it backwards. So the voltage, the B field ends up going by 0 at a much earlier point. That means the EMF across the coil would go to 0 not at 90 degree, but even before. Right? What does it mean? We have shifted the voltage backwards in time. So instead of the voltage going to 0 here, we have shifted it backwards by some angle delta x or something. Right? So the voltage is going to 0 much earlier. That means the current that follows would also go to 0 much earlier. Right? Yep, Jonah.
Is there any problem with that because now the voltage isn't 0 like at 90 degrees, or is it just the current that matters?
It's the current that matters. The voltage not being 0 is going to be problematic because we are going to be shorting it, right? And the short is going to be having maximum amount of contact with both the brushes at 90 degree. So that is still the point where it's going to be shorted. You can't make this voltage arbitrarily large at this point because that will damage the brush. But given a brush that can handle some amount of voltage across it, you can compensate away for the current. Even if you use the resistive graphite brush, as we saw on this curve, it would still have some component of current that is not quenched fully, right? You can quench that component fully and make it go to have a full proper commutation by using this. But that will come at the cost of having a slightly larger amount of current going through, circulating current going through the coil that's being commutated, because there is some amount of voltage that's being put at that point when it's being made, right? So you can not only do for any current, you can also compensate for LdA by dt. There is one thing interpoles cannot compensate for, which is the demagnetizing effect of this current due to the armature current, the magnetic field getting reduced in the magnets. So for that, what we use is compensation windings. Basically, we have conductors here. On the pole face. Such that the current in these conductors, so this is the north pole sorry, this is the south pole, this is the north pole, right? On these pole faces, we have slots in which there are additional conductors which are carrying current in such a way that the current in this conductor is exactly opposite of the direction of the current going in the conductor on the rotor. So what would that mean? Whatever magnetic field this is creating is exactly cancelled out by this conductor. Right? They are in very close proximity. Here I've drawn it in an exaggerated manner, but the LG is very close to zero. Right? It's like 0.2 millimeter or so on and so forth. So it's a very tiny, tiny distance. So especially in large motors, this distance is quite small. So this conductor, whatever this B field is creating, is going to be exactly cancelled out by this B field. So the only B field that remains is whatever is due to the magnets. Right? The rest of the B fields are fully cancelled out by the compensation winding. So compensation winding can handle any amount of current that we have, and it can still create the magnetic axis at 90 degree, and it can also compensate for field weakening. Which comes from demagnetizing effect of the cross-magnetizing field. Right? And especially in very large motors, and this is quite expensive structure because in case of our low power motors, when you have magnets, of course, you can't do this. You can't drill holes in the magnet and try to put conductors in them, it won't work. So you would have a field wound motor where the magnets are electromagnets, and then in the slots of the, you'll have slot on the stator structure itself where you can put additional conductors, which end up being quite expensive to create and then have this structure. But it's worth it when you have very large currents. Right? When you have very large currents, you cannot use graphite brushes. You just have to use copper brushes. And in that case, the LDA by dt would be extremely large. So this added effort of putting these windings to compensate for it would be well worth it. Okay. Any questions? Okay. So this content is not covered in the book. I won't ask this in the extra exam. This is particularly not too useful concept going forward because DC motors, as I said, are being phased out. So in your real world, when you go to industry, there's very high likelihood that you would never see this or use this ever again. But just for completeness, I wanted to cover this topic so that you get an idea of why DC motors are not popular. Right? It has all of these problems and it has these elaborate methods to fix them. And when we look at AC motor, it will become clear that all of these problems do not occur in the first place, because we'll take the winding and put it on the stator instead of the rotor, and that solves a whole bunch of problems, right? Okay. So with that, we are done with the structure of DC motor. We are going to be looking at the equations for a DC motor, and then we'll look at how to do a control of DC motor. Okay, we have 5 minutes. Okay, so last week we derived the expression for the torque and the expression for the EMF of a DC motor. So we started off with the hypothetical case where we just had this coil in air gap without an iron core, and we figured out what the torque due to that one coil is going to look like. And at angle alpha equal to 0, when it's planar to the magnetic field, torque would have been maximum. And when it's at 90 degree, all the force would have been perpendicular, there would have been no torque. So this is the torque of one coil. And then the EMF structure has the same thing, because when it's at 90 degree, flux would have been 0, but d phi by dt would have been large. And the EMF across the coil. Now, then we did is we said, hey, we can put one more coil which is at 90 degree because this has too much ripple in it. Right? If this is going to go to a motor, it's going to cause a lot of oscillation in the speed because the torque is varying a lot. We can resolve it into harmonic components using Fourier, and there'll be a whole bunch of higher order components which is going to cause the rotor to oscillate too much, vibrate too much. So what we said is, why just have one coil? We can put one more coil. Say 90 degree away, and that is going to have its own torque curve. So this is at this angle, this is at some other angle, the angle between them is 90 degree. And the net torque, if these coils are conducted in series, initially we first saw the case where these coils are in parallel and the commutator segment is going from one coil to the other, which would then be problematic because we're interrupting current and so on and so forth. So that's when we did the lap winding, when we had one coil, we took the same coil and made the connection for the next set of winding. And then the same coil, so that these coils are connected in series. So it is not just one coil that's producing the torque, it's both of these coils that are producing the torque now. So the net torque would be the summation of these two. This is what the torque look like. And when we add more and more coils, it is going to have a much better with higher values as well, to the point where it almost looks flat, right? So this was for the case of a hypothetical system. In case of a practical motor where we have an iron core, this is no longer going to vary in this sinusoidal fashion, because the B field is perpendicular at every single point on the conductor. Right, so let me look at this case where I have a conductor here, right? And then there is a B field perpendicular to this. What is going to be the component? So you have a current coming out, you have a B field going in, the torque is going to be L times I cross B, so it's going to be B. So that's going to be the force, and the force is all perpendicular to the current carrying conductor, perpendicular to the tangential to the surface of the iron core. So the force is all going to be tangential. So all the forces tangential. Right? There is no component that is pulling the conductor out. In the previous case, when we had just a magnet and we had a conductor here, right? We would have had a force which is perpendicular. So this is the current carrying conductor, this is this. So the force would have been like this. Right? You can resolve that into one component, which is tangential, F tangential, and then one component which is F normal. So only a component of the force was contributing to the tangential which is rotating. Some of the component is still the force which was compressing the windings or expanding the windings. This wouldn't happen when we put them in the iron core because all the field lines end up being perpendicular. So the torque on that particular winding, let's say it's some radius r, and the length of the conductor rotor core, let's say extends all the way to L. Let's start off with the force equation. The force experienced that by the conductor would be L times current in the conductor times the magnetic field due to the magnet external magnets, right? B magnet. Okay, so what is going to be the torque? Torque is just going to be the radius times the r cross F, and all the component is perpendicular to the r, so it's just r times F. So we end up with R L I times B of the magnet. That is just for one conductor. What is going to be the torque due to, say, a conductor at some other angle? Some other random angle? Will it be the same torque or will it vary with angle? So I calculated the torque for this conductor. What would be the torque for this conductor on the top here? Would it be the same or would it be different? You said same, right? Perfect. So because again, the magnetic field is perpendicular at every single point. It doesn't matter where the conductor is, the magnetic field is perpendicular to it, right? So it's going to be exactly the same. So if I have NC number of conductors, this is the total number of conductors. So if I go to this rotor, and each slot, let's say, has 10 conductors, and then the next slot has 10 conductors, there are 12 slots, there will be a total of 120 conductors, right? So the total torque is going to be the total number of conductors, NC times R times L times I times B. What is the relationship between this current in the conductor versus the current coming from the external world? Is this current same as the DC current? Is current in each of this winding that I have inside same as the current that comes into this wire, external wire? Ganesh is saying yes. Anybody else?
Would there be a resistive loss?
Even if there is a resistive loss, the voltage would be different, but not the current. Right? KCL would dictate that the current can't go anywhere else. Assuming there's no capacitive leakage, we are going to ignore all of those. Right? Okay. So we need to be careful here because when I drew the winding diagram, that's why the winding diagram is very helpful. Our brushes here and our other brushes here. So if you remember in the lecture on the where I shared the PowerPoint, if there's 20 ampere coming into this, what is going to be the current in each of the windings on the left and the right branch? 10 and 10, right? It's going to split equally. 10 ampere, 10 ampere. So this I here is the current in the conductor. The current in the conductor is half of what the current is coming from the external world. Right? So this I is actually I from the external world divided by 2. In our case, we are looking at a 2-pole simplex lap wound machine. So the number of parallel pathways is 2. If you have more number of poles for a lap winding, for a wave winding, the number of parallel pathways will always be 2 for a simplex wound wave winding machine. But when you have lap wound machine, the number of parallel pathways will be the same as the number of poles. And when you have duplex winding, the number increases as well, double it. Right? The parallel pathway starts to increase. So instead, we will write this as I divided by M, where M is the number of parallel pathways. Right? I'm going to take just 3 more minutes. Those of you have to leave, that's absolutely fine. Again, it's recorded. Let me do the equation for the EMF as well so that we can do the Simulink modeling next lecture. Okay, so our expression for the torque ended up being NC by M, total torque R times L times P of the magnet times the current coming from the external side. So this whole term is a constant, which we are going to call KT, torque constant. Now let's quickly look at what the EMF is going to be. Maybe you remember the case where we derived the EMF for the structure, which was moving at some velocity V and there is a magnetic field B. Anybody remember what the EMF across this was? Let's say this is some W and the width can change and the rod length is L. Anybody? How do we go about deriving it? Again, I don't remember the formula either. What formula can be used to derive the EMF? Whenever I say EMF, there's just one formula that you need to remember, which is what was it?
The change in flux.
Change in flux. So d phi by dt, right? And the flux itself is going to be B times T by dt. B times the cross-sectional area, which is W times the length, right? B is fixed, the L is fixed, B and L comes outside. dW by dt is going to be the velocity U. So BLU, right? So if you have a current carrying conductor moving at some velocity V or velocity U, so this is moving at some velocity U in this direction, and there is some magnetic field B and they have some length L, then the EMF is just B times L times U. So our EMF, let me write it here, EMF of that one conductor is B times L times U. Okay. So this is for NC conductor B. If I want to look at for the total, what is it going to be? What will be the EMF for all the conductors? That is just for one conductor, right? What will be the EMF for all the conductors? What would I multiply it with? Let's say the number of conductors is NC. What was it? How many of you say NC? How many of you say something else? It would be NC by 2, right? Again, if you look at the voltage across this, these two set of windings are in parallel. So if there are 100 conductors total, 50 conductors are series here, 50 conductors are series here, the next 50 are in parallel. So it's not going to be NC, it's going to be NC by 2. NC by 2 is going to be the E total. This itself, U can be replaced as R times omega, right? We have already seen that before. So again, our E total is going to be R times L times, NC divided by 2 times R times L times B times omega. B again is the magnet B field. So when we had 2 parallel pathways, NC by 2, if we had more parallel pathways, let's say some M parallel pathways, only the conductors that are in series matters for the EMF. So NC by M. If you look at the term, it's again the same constant, KE, which is exactly same as KT, right? Assuming that these two are the same units. Okay? Let me just write down all the equations together so we can carry it from there next class. Anybody has any questions so far? We have everything here that we need to know to control this motor going forward. So our electrical system equation is going to be, we apply some voltage across the terminal of this motor. So V is the voltage that I apply here. And then some of the voltage is going to get dropped in the resistance. right? R times I. Sum of it is going to be the L dI by dt. Current flowing through, because there's a whole bunch of coil on an iron core, it's going to have quite a bit of inductance, as we'll look at when we estimate the parameter for the motor. And then finally, what is going to be the other component? How will I complete this equation? What is the one missing term?
EMF.
EMF. Perfect. And then we have our mechanical system, which we already know. Our electromagnetic torque is equal to the load torque. We have looked at this a dozen times. J d omega by dt plus b omega. So this is the electrical world. This is the mechanical world. They don't like to play together. But then we have our beautiful set of two equations. This is the torque, is kT times I, and then the EMF is Ke times omega. So all we learned, 2 weeks we spent learning electromagnetic theory is just to get these two equations, right? So that we can marry the electrical world to the mechanical world, so that we can create the electromechanical motor. System. So we can transfer power from the electrical system to a mechanical system, or the other way around, if you're doing a generator from the mechanical system to the electrical system, with the Maxwell's equation, all the 5 equations basically boiling down into these two simple expressions that we have. Right, with that we are done. Next class on Friday, we'll try to figure out how to model this mathematically. You are unusually quiet today. Any question? Your PowerPoint, right?
Yeah, I was trying to figure out how to do it digitally. Is there like an easy way to do it, like drawing on No, I was thinking of getting one, but.
Okay. Yeah, or just use it, put it in Paint, right?
Okay, yeah, I could do that. I don't have like a mouse either, so it's hard to draw.
You can even do it in Word.
Yeah, okay.
You can just put lines in Word with different colors.
Yeah. Okay, I was thinking of doing that.
Yeah, or just mark it.
Okay, yeah, I'll just upload it and if it's not clear, let me redraw it. Thank you.
I have a question.
Yeah. I was in an office job before.
LG is,
Oh, well. Can we get to the next slide? Definitely get to the dog days of school, so.
so when we have this pathway for, let's say, conductor here versus conductor here. So there's two pathways, one through here, one through here. One pathway through here, one pathway through here. So this pathway is longer for this one, while this pathway is going to be the same. So you can think of it as two sets of resistance, right? One resistance here, one resistance here. The net resistance is the parallel combination of these two.
Okay.
So this and this, even though these two pathways are the same resistance, this pathway is offers a little bit smaller resistance. The one closer has a much more better pathway.
Okay, so because of that, that's why there's a disconnect.
Yep, in the saliency we have this LG pathway actually is the maximum at this point.
Oh,
Towards these points, there's other pathways for which it can lead to.
oh, okay, thank you, that's helpful.